In this video, we will learn how to derive demand functions for labor and capital given the production function. The question is, given the production function of a firm is, we have to maximize the production function, which is a function of labor and capital, which is equal to L raised power delta plus K raised power delta whole raised power 1 upon delta, subject to the constraint that is total cost is equal to wage rate times units of labor plus rental rate of capital times units of capital. We want to maximize this production function subject to this constraint, and we have to derive the demand functions for labor and capital. Okay, so what we have to do, we want to maximize, that is, we want to maximize our production, that is Q, which is a function of labor and capital, which is equal to L to the power delta plus K to the power delta whole raised power 1 upon del. Subject to the constraint, we have the constraint that is C is equal to W times L plus R times K. Okay, so how do we solve this kind of question? First thing is, we will form the Lagrange's function. And how do we form the Lagrange's function? There are some steps. First, we set this constraint equal to 0, that is, we write C minus WL plus RK, and we set it equal to 0. The next step will be, we multiply this resulting constraint both sides by lambda. So here we also lambda, so lambda times 0 will be equal to 0. Then our Lagrange's function, and let me write it here. What will be our Lagrange's function? L will be equal to, so Lagrange's function will be equal to the production function, what we call the objective function, that is the aggregate of the production function and the resulting constraint, that is L raised power delta plus K raised power delta whole raised power 1 upon delta. To this we add the resulting constraint, that is lambda times C minus WL plus RK. Okay, to find out the optimal values for labor and capital, what we do here, we partially differentiate this Lagrange's function with respect to labor, capital and lambda, set them equal to 0 simultaneously and solve them. Okay, so first we take the partial derivative, that is L subscript L, that is the partial derivative of this Lagrange's function with respect to L. So if I take the derivative of this function with respect to L, I will get, so first we apply the power function rule, so 1 upon delta will become coefficient, we have 1 upon delta, then we have L raised power delta plus K raised power delta, and exponent is subtracted by 1, so it becomes 1 divided by del minus 1. Then we apply the chain rule, that is del upon del L of this function, that is L raised power delta plus K raised power delta. Okay, so simple thing what I am doing, since I am differentiating with respect to L partially, first we apply the power function rule, so exponent becomes coefficient and exponent is subtracted by 1. Then we differentiate whatever is in the bracket, so we have del upon del L of the derivative of this L raised power delta plus K raised power delta. Okay, and what will be left here? So the derivative of C will be equal to 0 because we are taking partial with respect to L. Derivative of L will be equal to 1, so we are left with minus W lambda, or I can write minus lambda W, and derivative of this term will be equal to 0 because no L is involved, and we set it equal to 0. Okay, and if I arrange it or solve it further, so I will get 1 upon del, then we have L raised power delta plus K raised power delta, then we have raised power 1 upon del minus 1. Now the derivative of L raised power delta, again exponent becomes coefficient and exponent is subtracted by 1, we will get delta minus 1, and derivative of this will be equal to 0 because we are taking the partials with respect to L, minus lambda times W, and we set it equal to 0. Okay, by the same logic, when we solve, when we take the partial with respect to L subscript to K, means the partial derivative of this Lagrange function with respect to K, what will we get? We will get 1 upon L, and you can do it, I can do it here, but it will take time here. Okay, so it will get lengthy. So likewise we will get R raised power delta plus K raised power delta whole raised power 1 upon delta minus 1, and here in place of this we have delta L raised power delta minus 1. Here we will get K raised power delta minus 1 minus lambda times, so in place of W we will get R here. Okay, you can solve it, no problem, and we set it equal to 0. Okay, to save the space and time here, I have actually done it here. Okay, let me see if I am visible on the screen also. Okay, up to this it's fine. Now we need to take the partial with respect to lambda of the Lagrange's function. So since no lambda is involved in the first term, its derivative is 0, so derivative of lambda in the second term will be 1, so we are left with C minus WL. Here it is minus, sorry. Okay, so we have minus RK and we set it equal to 0, and I can write it in this fashion, that is C is equal to, if I transpose it here, C will be equal to WL plus RK. Let us say this is equation first, equation second, and let us say this is equation third. Now what we need to do here, first thing is we solve equation 1 and 2. That means we divide equation 1 by equation 2. Okay, so here we can do one thing also. If I transpose this minus lambda W to RHS, it will become plus lambda W, and here also if I transpose lambda R to RHS, it will become positive lambda R. Okay, so I will not do that very stuff here. So let's divide equation first by equation second. So we will get, so what is equation 1? That is 1 upon delta, then we have L raised power delta plus K raised power delta whole raised power 1 upon delta minus 1. Okay, and here we can also do one thing, this delta and delta gets cancelled, and here this delta and delta gets cancelled, so I will not write this very stuff here to save the space. So we have then times L raised power delta minus 1. To this we divide by this equation, that is L raised power delta plus K raised power delta whole raised power 1 upon delta minus 1, and here we have K raised power delta minus 1, which should be equal to, if I transpose this here, it will become lambda W upon lambda R. Okay, so here we can do some cancellation, so this term and this term will get cancelled, this lambda and lambda gets cancelled, we are left with L raised power delta minus 1 divided by K raised power delta minus 1 is equal to W upon R. Now let us solve this for K. So what will we do here? So if I transpose it here, we will get K raised power delta minus 1 times W upon R is equal to L raised power delta minus 1, or we will get K raised power delta minus 1 is equal to, transposing this, it will become R upon W, then we have L raised power delta minus 1. If I transpose the exponent, it will become exponent but in reciprocal order. Okay, so what exactly will I get here? So I will get K will be equal to R upon W whole raised power. If I transpose it, it will become 1 divided by del minus 1, and then we have R raised power del minus 1, and when I transpose it, it will become 1 divided by del minus 1. Okay, so further solving, here you can see, if I can write it properly, so it is L raised power delta minus 1 times 1 divided by delta minus 1. So these two terms get cancelled, we are only left with L here. Okay, So let me rub this out, which implies we will get K will be equal to R divided by W raised power 1 upon del minus 1 times L. Okay. Now we need to plug the value of K is equal to this stuff into equation third. Okay. Doing that very stuff, what will we get? So we will get C is equal to W times L plus R times the value of K which we got here, R divided by W raised power 1 divided by del minus 1 times L. Okay. And we need to solve this function for L. Okay, let's take first L common here. So we will get C is equal to L, and here we are left with W plus W plus, so we will get here R, and let me write it here R. If I expand it, it will become R raised power 1 divided by del minus 1 divided by W divided by 1 divided by del minus 1, sorry, W raised power times L. Sorry, L we have taken out, there is no L involved here now, which is equal to, if I simplify it, so I will get L times W plus R into this stuff. So this are same, we can add the exponent, so we get R times R is power 1 divided by del minus 1, so it will become, so bases are same, we can add up the exponents. So we will get R is power 1 plus 1 divided by del minus 1. So doing cross multiplication to the exponent, so we will get del minus 1 plus 1. So we will get here R is power del minus 1 plus 1. So this gets cancelled, divided by 1 into del minus 1. So we are left with del divided by del minus 1 is the exponent of R. Okay. So I can write it here. R raised power del divided by del minus 1. Okay. Then we have here W raised power 1 divided by del minus 1. Solving for L, that implies, so C is equal to this very stuff, or I can write L will be equal to C divided by, okay. Let me first simplify it here. So doing cross multiplication, what will we get here? So L, we get W times W raised power 1 divided by del minus 1 plus R raised power W divided by del, sorry, R raised power del divided by del minus 1 whole divided by W raised power 1 divided by del minus 1. Okay. So again, what will we get here? We will get, let me see if I am visible. Okay, I am visible here. So we will get L. Again, this stuff will become W raised power del divided by del minus 1 plus R raised power del divided by del minus 1 divided by W raised power 1 divided by del minus 1. Okay. So this is equal to C. So solving for L, so L will be equal to C divided by this stuff. Okay, so we will get W raised power del divided by del minus 1 plus R raised power del divided by del minus 1 divided by W raised power 1 divided by del minus 1. Okay, so simplifying it again, so we will get the demand for labor will be equal to if we reciprocate it, we will get W raised power 1 divided by del minus 1 divided by and we have obviously C also here, divided by W raised power del divided by del minus 1 plus R times del, sorry, R raised power del divided by del minus 1. Okay, this will be, and let's write it here, this will be the demand for labor. Okay, when I plug the value of L is equal to this stuff in this equation, I will get, and likewise you can do it properly. So demand for capital will be equal to, and let me write it here, I have the space, so let me write it here. So K will be equal to demand function for capital will be equal to R raised power 1 divided by del minus 1 times C divided by W the raised power del divided by del minus 1 plus R raised power del divided by del minus 1. So this is the demand function for labor, and this is the demand function for capital. I hope I make myself clear in this video. Thank you.